Fire
Okay, so hi everyone, I'm Emile Pankburn, member of the French team, and I'm going to present the subject burning bottle. So the problem is it possible to cut glass bottle in two pieces using a string, fire, and cold water? And as you see here, it's possible. But we decided to use a resistive wire in order to have a better control on the temperature. So we'll try to investigate what the physics behind this effect, if you can optimize it, and if it's possible to cut a shape in a glass more complex than a straight line. So here is our experimental setup. So we have a voltage generator to inject intensity, to inject current inside the resistive wire. And so with the resistive wire, we heated locally the bottle, and then we cool down the bottle in water. This creates a thermal shock. And so by varying intensity, we have a high precision on the temperature of our resistive wire. So let's just have a video of the effect. So the fracture will appear approximately around this zone. So as you see, when you slowly cool down the water into water, it creates a fracture. So let's have an intuitive explanation. So here is the exterior surface in contact to water, and here is the exterior surface of the bottle. And so because of the cooling by water, the exterior surface cooled down, and it contracts because of thermal expansion, but the internal surface is still hot, and so it creates stress. That means we will have tensile stress on the exterior surface and compressive stress on the interior surface because the interior surface is still elongated. So let's have some equations. So the elongation is proportional to the difference of temperature, and the stress is also proportional to the difference of temperature. We have fracture if the stress is superior to the maximal stress the material can sustain, and is defined a critical temperature for the thermal shock. The gradient of temperature depends on the thermal conductivity. So diamond glass that we studied in our work have a low thermal conductivity, and that means that we will have a high temperature gradient. That means a low thermal shock resistance. So we use a simple theoretical model. So it's a 1D model. So it shows the thickness of the glass bottle. So we use glass conduction equation to show the glass bottle, and a boundary condition. So if the glass bottle is in contact to air, water, we use convective boundary condition. And when the glass bottle is in contact to the wire, we say that the bottle is at the temperature of the resistive wire. So here, two simple diagram of the temperature field we can obtain in the heating phase and the quenching phase. And so we can obtain the temperature field. And with this temperature field, we can calculate the stress field by assuming the stress is proportional to the average temperature minus the temperature field. Because stress is a key parameter in this problem, we decided to visualize it using a polarizer and an analyzer. And so when glass is heated non-uniformly as in our problem, stress will arise, and stress can change optical index. We assume sigma 2 here is 0 because of translational symmetry along the wire, so there is only sigma 1. And you can show that the rotation between the two polarization components along this axis and this axis is proportional to the stress. That means by determining the retardation, you can obtain the stress up to a proportionality constant. So how to obtain the retardation? Actually, just by looking at color, it's very simple. So thanks to this Michel-Levy color chart, by looking at the color of the bottle, you can obtain the retardation. And so here is two photographies. So here there will 11 ampere flowing into the resistive wire, and here 5 ampere. And you see that with 11 ampere, you have more retardation than at 5 ampere. And that means more stress. That is qualitatively what we expect. And if you want to be more quantitative, we plot the theory against the experiment, and we have a good agreement. We just rescale the experiment because, as I said, we obtain only the stress up to a proportionality constant. So now let's talk about the initiation of the fracture. So for brittle materials like ceramic or glass, the total energy is equal to the elastic energy plus the fracture energy. Okay, so A here is a pre-existing quark length, but because all real material have some flows. And if the stress becomes sufficiently high, it will become energetically favorable for the material to increase the quark length, the pre-existing quark length A. That means a fracture will form. And so this critical stress is given by this formula. And so with this photoelasticity analysis, you see simply that strain energy is released with fracture. So this color means that there is more stress than this color. And so you see after a fracture, we have less stress. So less elastic energy. And this graphic also shows that qualitatively, when you initiate when you try to have a fracture with initial fracture, it's a lot easier to have a thermal shock fracture because you increase the pre-existing crack length height. So now let's study the fracture section. So we analyze the fracture section with a polarizer microscope. And so we have beautiful observation, but can we have a quantitative analysis? So a simple convention for the next two slides, the top of the photography will always be the interior of the glass bottle, and the exterior will be at the bottom. So, as I said, there is compressive stress on the interior surface of the glass bottle and tensile stress on the exterior surface of the glass bottle. And with this stress field, we typically have this crack front shape. And so, when we observe it with the polarizer microscope, we typically obtain these images. So these are beautiful images, but can we have more physics associated to it? And in fact, yes, we can. So these are mixed cycles, so they are marking on the surface of an accelerating crack, and these are Wallner line, and this gives the crack propagation direction. So how does Wallner line form? They form because the mist, sound wave can originate from the mist and velocity cycle, and a Wallner line is then created by the interaction between the sound wave and the propagating crack front. And so you obtain the Wallner line you see here. With this Wallner line, you can in fact calculating the crack propagation speed. So the exact description of the crack front shape is very complicated. So we assume it's a quarter elliptical shape, like this one here, and we can measure the crack propagation speed in our experiment with a thermal shock. Theoretically, the maximal crack propagation speed is 0.38 the speed of sound in the material, and we find experimentally that this ratio is equal to 0.40 plus or minus 0.43, so we have a good agreement. Now let's talk about oscillatory cracks in glass. So here is our experimental setup. So it's really simple. We uniformly heat the glass and slowly cool it down in water at a speed v, and we see that the fracture will start to propagate, and the front will always be at the interface between the water and the heated glass. To initiate the fracture, we made a tiny flow at the bottom of the glass sheet. So let's have a theoretical model. So we use the maximum Hooke's stress criterion. That means the crack will grow where the maximal potential energy is released. So this is a computational computation of the temperature field in our glass sheet. So here is the cold part in contact with water, and here is the hot part in contact with air. And you see that there is a temperature gradient between these two areas. That is where the maximal stress will be. As I previously said, there is tensile stress on the cold part and compressive stress on the hot part, or the hotter part. It's easier to expand near the edges. That means there will be less stress at the edges. And so, as you see in this photography, the crack will not propagate near the edges because it will release less potential energy. So as you see here, the crack is pushed back by the edges because it releases more potential energy at the center of the glass sheet. So let's have some experimental results. So when the crack is curved, the symmetry between the two parts around the crack is broken. That means there is a jump in temperature across the crack. So here is a video of the phenomenon. So, as you see, when the temperature is low, the crack is straight and there is no temperature jump. But at a higher temperature, when the crack can be curved, and you see with this color that there is a jump in the stress field, and so a jump in temperature. What's the physics behind this effect? So when the temperature is sufficiently high, the stress path is no longer stable, and the crack will deviate from the straight path. But when coming near the edges, it will be less favorable to propagate near the edges because it releases less potential energy, and so the crack will return at the center of the glass sheet, and so we will see some oscillatory motion. So in conclusion, we have a quantitative and a microscopic comprehension of the physics of a thermal shock. We understand the crack initiation, that the crack initiation is a key parameter in the problem, and we also understand the physics of an oscillatory crack. So in conclusion, burning bottle and cutting glass is very successful. Thanks for listening.
Thank you very much. It is great, and thank you for being on time. Now we can move to the clarifying question from Brazilian team. Please come up with them.
Hello, please come back to slide 7. Let's go in chronological order. What is the lambda in the path difference?
It's a wavelength of the light.
Oh, okay. That is the retardation. Okay. Slide 8, please.
Sorry?
Slide 8, the next one. On the top right graph, what is the bottom axis represent?
The retardation.
Okay, this is the retardation, and the up axis.
Thickness here, but we do not use it. It's the thickness of the glass.
Okay, but what is on the top of this graph? There
it's actually
scale there.
It's also the retardation.
Okay, so are different units for the retardation?
I don't know.
Okay, slide the next one, please. Well, how did you initiate the fracture?
In this problem, we initiate the fracture with a thermal shock. So you heat locally your glass bottle and then you cool it down in water.
Okay, but so what's the difference? How did you measure with or without the initial fracture?
We increase the size of the natural flow in glass by just made macroscopic flows at the surface.
Okay, thank you. And slide 12, please. Could you clarify how you did the measurement of the velocity of the crack?
Okay, I think it's easier to visualize with this diagram. So you know the velocity of the sound wave. You assume you know the velocity of the sound wave in glass, and you know this crack, the shape of the crack front. Okay, and so by knowing the form of the Wallner line that you observe, you can determine the velocity at each point, and you can after then verify that at each point you obtain the same speed.
Thanks for your presentation. It was a really nice presentation. You showed a lot of physics of the problem. So here's the problem statement. I would like to point out something. The problem statement asks us to optimize the effect, investigate the physics behind the effect and optimize it. And it asks us if it's possible to cut out a shape in the glass that is more complex than a simple straight line. So here are the good points and the points that need some patience from our part. They used a good experimental setup with using a lot of equipment and creative modes of exploring the physics. The use of polarizers to understand the stress. This was a really nice point, a way to visualize what is happening with the material, and really nice explanations of the crack. When they used the glass plate to understand the crack movement using the different stress in the regions of the glass. That was a really nice point. Some points that we think need some attention is the lack of geometry visualization of the cracks and how the stress in the glass how the stress in the glass changes with or without cracks. The problem statement talks about fire, so we think that should be some discussion of the difference of using fire and the resistivity wire that they used, although the idea of using the resistivity wire offers a better quantitative measurement. And another point is the optimization. They didn't talk about changing some parameters of the problems, like the shape of the bottle or the thickness of the wall of the bottle. So we think that these points need some some clarifications. So points to discuss is firstly that the statement mentions fire and they didn't explicitly use fire. So we think that this needs something to be discussed. They firstly said that the criterion for the material to get to failure would be the stress. However, when you are dealing with cracks and microscopic flaws on the material, the most appropriate factor to use is the toughness intensity factor, which is related to stress, but there are some difference that we think it would be a good point to discuss. The other thing is the optimization and how would they change some parameters of the problem to optimize the cut, and what they think what the optimization means in this problem. And changing some parameters, I mean like change the geometric shape of the bottle, the thickness of the bottle wall, the temperature of the resistance wire, the temperature of the bottle of the water. Sorry. So these are some points, but I would like to thank you for your presentation. It was really nice and some really beautiful images, and I'd like to continue for the discussion. Oh, here are final remarks. They have a good phenomenological discussion. However, it was we think that it was missing some optimization. Can you?
I just share my screen. Oh.
While you do that, I'd like to start. The problem statement mentions fire, and you didn't use fire. You had something different. Do you think that what do you think are the main differences between the resistivity wire and the fire?
So we didn't choose fire because you cannot control of knowledge. You cannot control the temperature of the fire. It's more complicated. That's why we choose a resistive wire in order to show the influence of temperature and how to optimize then the temperature to have a better crack. And
okay,
I think for
go on. Sorry.
Fire, you will use more energy, I think, to obtain your crack. So if you talk about optimization, maybe it's better to use the resistive wire. And
did you make some measurements to affirm this?
No.
Okay. I'd like to point out something. I agree with you that resistivity wire it's a better quantitative measurement, offers a better quantitative measurement, but however, it will be possible to infer the temperature using like a temperature camera. Don't you agree?
Yes, but do you have some gradient of temperature on a fire, and maybe you measure only the exterior temperature of the fire? So I think it's more complicated than just measuring the temperature of the resistive wire. But if you have done that, I think it's great.
Oh, sure, I agree with your point. Another thing, what are the main differences between the fire and the string?
I think one other main difference is that maybe you will have a gradient stress that is more important for the resistive wire because we heated more locally the bottle. So also in terms of optimization, I think the resistive wire is a better idea. But I don't know what you think about this.
Mm-hmm. I agree in parts with you. But I would like to move on to the optimization part of the problem. I feel a lack of parameters changing to find a better optimization for the problem. How would change, for example, the thickness of the bottle wall?
If you decrease the thickness, in fact, you will have a stress gradient that will be less important, because if it's very thin, the low thermal conductivity of glass will not have an important effect. But if contrary, if you have a very thick wall in your bottle, you will have a much higher temperature gradient, because the internal wall of your bottle will still be at very high temperature, whereas the exterior surface of your bottle will be at very low temperature. So that means it's easier to work a thicker bottle. Do you agree with that?
I'm sorry, I didn't get the last part.
Okay, so if you have a really thick glass thickness, okay, because the internal surface of your glass bottle will still be at a maximal temperature, whereas the exterior surface will be at the temperature of water.
Oh yeah, I agree with you. The higher if the thickness is bigger, it's easier to get the fracture of the material. How do you think that the time dependence of the problem is? I'm talking about the heating process of the bottle.
Okay, it's in fact because we have a low thermal conductivity. I think if you will want to be at equilibrium, you can. It's better to wait some time, and so maybe with fire you have less control about that, because I don't know if you have done the experiment, but you cannot maintain the fire for for a very long time. Whereas with a wasty wire, you can be sure that you are at equilibrium, I think.
Okay.
But do you agree, or you have some?
I'm sorry, I didn't get the last part. Again.
You agree with that, or maybe you have another idea about that? I don't know.
No, I agree with you. I did the experiments. However, I think there are a little more detail about the time thing, but I would like to move on to another thing. The statement asks us to try to make different cut shapes on the bottle. Did you try to do something like that?
From this point, we can add team members to the discussion.
I think it's different shapes, and if you look closely at the subject, it does not ask about bottle, but about glass. So I think it's answer the problem perfectly.
Oh, okay.
If you would have any member of team who want me to give you words, please type it in the chat.
Okay, maybe you're right about this. It is an interpretation issue. However, I would like to ask you: do you think that it is possible to cut more complex shapes in a bottle?
Yeah, I think it's possible, and it actually be the same experiment have actually been done in the literature with a flask. So I think it's more close. It looks more similar to a bottle. Donc I believe this same type of experiment is perfectly possible using a bottle. And again, if you use this.
Okay, but what kind of you made a point on this slide that the edge makes a really important effect for the cracks to make this curved path. How would a bottle is edgeless?
Yes, I think it's a much more complicated. In fact, it's why we don't have studied this with a bottle or flask. It's because it's much more complicated, because we don't have the edges, and it's the different fracture that you will have more fracture, because at one point a lot of fracture will initiate from this point that you fragilize with this initial flow. Sorry. Mm-hmm. And so the different fracture will interact between themselves, but to understand that it's much more complicated. I think you should use a finite element method to understand that properly, to have the stress field at every time. And so I think it's not.
I think that
there is Anderson wants to ask question. Yeah, please fire away. We don't hear you, Anderson.
You are muted, Voot.
Am I talking now?
Yes.
Yes.
Okay. Louder, maybe.
Really nice presentation. Thank you. What about these cracks? Did you do these cracks with the wire in the same way you did with the bottle, or you just made a little crack and heat it up and cool it down?
Sorry, can you just speak louder? I cannot hear what you say.
Sorry, can you hear now?
Yes, it's better. Thank you very much.
Okay, sorry. So these cracks, did you do these cracks with the wire, or you did a small
no.
initiate fracture and then heat it up and cool it down?
Yes, just a tiny flow at the bottom. Without a wire, you don't have to use it. It's like cracking an egg with a hammer, you know.
Okay, thank you.
I think
Thank
Anna
you.
wants to make a
Anna
question.
has a question. Yeah, please, Anna, fire away.
Hi, thank you for your presentation. It's very nice to discuss this problem with you. I just want to ask if you vary the thickness of the wire and could evaluate if it's better like one turn wire or like 2 or 3 turns. Does it affect the
Yes.
cut?
Sorry, you are finished?
I have one more question, but you can answer this and then I come back.
Okay, sorry, excuse me.
Let's
In
do
fact,
one by one. Yeah.
in fact,
Okay.
yes, we try to do that, but we could not, because our wires were conductive, we could not make them touch together. But when they are really close, it's like one wire, because I think there is a like thermal diffusion length, and if you are below this point, it will be like one wire. But the consequence will be that you will have less stress because you will expand the area when you hit the water.
Okay. The second question is, I think it should be more clear. I think I did understand very clearly what for you is a good cut. I mean, if it has angles, or if it is distant from the wire, or if it has cracks. How do you define a really good cut? Because you said it was very successful. So what parameters did you consider to say that?
If we consider not a good cut, because maybe it's more clean, you know. So I think this one, we say it's a good cut, and a good cut should be all around the bottle, not just, you know, at a fraction of the bottle. That means you should cut the bottle. And to have the better cut, you should use not too much intensity. So if you use too much intensity, you will have this kind of shape. And so to do that, because if you do not use if you do not use enough intensity, the crack will not propagate around all the bottle. And so you have to make a tiny flow at one point, and it will help to have a cleaner fracture and a good fracture. So.
Thank you.
So
we need to stop the discussion at this point. We run out of the time. We give now word to the reporter for the concluding remarks.
So I thanks a lot the opponent team, because I think they point out a lot of interesting elements in the discussion. So, for example, I have not studied very intensively how this physics depend on the thickness of the glass bottle, and I think it was an interesting point to raise. Again, the use of a different method to heat the bottle, like using a string and fire, was also very interesting, and also using maybe 1 or 2 rounds of the with a resistive wire. And finally, I think it was very nice to precise what we mean by a good cut, because I have to acknowledge I have not really explicitly said what was for me a good cut. So thank you very much.
Thank you for your report. So I have the question. You have said you understood and finally explained what was your criterion of optimization? Do you have some quantitative value and procedure to obtain these metrics that you will optimize?
For the initial crack length, we did not measure precisely how long it was. I think we should have done with a microscope. So we just, like with a knife, cutting a bit of bottle. For the temperature, I mean, it depends on the glass because you have different thermal conductivity. But so you have to adjust the temperature to have the right one in order not to have too much like branching around the fracture. I don't know if I answered correctly.
So it was like the longest fracture, or what? The quantitative measure of quality.
A good fracture should go all around the bottle to cut the bottle because the question was to.
Okay, the quantitative value is like a qualitative criterion, but that you try to optimize qualitatively, or it was quantitative?
Sorry, I don't understand.
Did you have a number to optimize, or it was just an impression that this cut is good and another doesn't?
I think it's quite easy to say because when there is no crack branching like that, you observe you don't observe any crack branching.
Okay, I understood. That then all the fractures without branching you consider it okay, yeah?
Yes.
Okay, thank you.
Thank you. Let's give the word to Alexander.
Okay, my question is possibly to both teams because I didn't hear it in the discussion. Have you studied or considered studying the state of the material before the heating? Because we obviously know that there are different kinds of glass and different impurities there, and there is a preliminary heated glass which is more resistant to fractures. Have you some kind of study of these? First of all, of course, the reporting.
So you talk about tempered glass. So we decided not to study tempered glass, and we the glass we used were strainless at the beginning. And what we study is that you know, at the surface of the glass you have some tiny flow, and here is some microscopic images that show where the crack starts the propagation, and it starts at the flow, like, as I said. And so here it's a proof that there is some flow at the surface of the bottle that initiates the fracture, because flow are more common at the surface.
Okay. Does anybody have something to add to this?
Yeah, we, as you point out, studying the particular properties of the glass that we would use to make this experiment would be a great thing to do, because even very similar glasses can have very different parameters, such as thermal expansion coefficient and other parameters relevant to the problem. However, in my experiment, I didn't have the access to the university lab, so I didn't have the opportunity to make these measurements. But you are right to point it out.
Thank you. We have 3 more questions. Shall we move on to Alexei and I encourage participants to make short answers? Alexei, your question.
Yes, I was just wondering about the critical intensity that you have pointed out, I think on the slide number 9. Can you go there, please? So may you remind me one more time, what is this critical intensity that you define?
This one?
Yes. This is the same that is depicted on the plot with the yellow line.
Usually, does it relating to this figure? Is it related to this figure, you ask?
I mean, there is a plot on the bottom part of the slide, on the right part, with some yellow dashed line.
Yes. Okay. Yes, it's a minimal intensity we need in order to obtain a cut, and it's related to this critical stress, because the critical stress is related to the critical temperature, and because of with the resistive wire, we can relate the intensity with the temperature, so we can measure this thing. Yes.
And this value is theoretical, or you find it out in experiment?
I do not put number on it.
I mean, you put some line, and Does it come from experiment or from theory? I just didn't get it from the presentation.
This formula?
No, the line on your plot.
Sorry, excuse me. It's the experiment. It's a minimal intensity we need in order for the same type of bottle to cut it.
Do you have some predictions from theory on this value?
For theory, as I said, you should just relate this critical stress to the critical temperature, and then with the resistive wire, you can associate it with the critical intensity, and so you have the relation.
Okay, thank you for your reply.
Thank you. Shibrian, please, very short question if you can squeeze it.
Okay, then only one out of several which I had. So as far as I know, for some strange chemical reasons, bottles do have different colors. Have you tried to understand whether the bottles which have different colors do respond differently to your basically applied current, let's say? Thank you.
We did not study this extensively, but here you see that with a different bottles or different color, so we assume different chemical composition. You can vary, I don't know, the Young modulus, the thermal expansion coefficient, I point out the Brazilian opponents and the thermal conductivity. And so you have different thermal shock resistance, but we did not study it further.